Technical Guide to Casio Tone. Part 2, Basic Circuits, and Part 3, Adjustment. In Part 1, we will explain the tools required for repairing and adjusting the Casio tone and how they are used. When ordering these tools from Casio, please include the code numbers listed in the textbook. An oscilloscope is used to observe the waveforms generated by various sections and is indispensable for repair of the Casio tone. 100 MHz type is recommended. The horizontal axis on the screen of the oscilloscope indicates time, while the vertical axis indicates voltage. Both must be adjusted in accordance with the waveform being observed. The horizontal axis, or time, can be expanded or compressed using the sweep time dial. One grid on the screen is used to display the time to which the dial is set. Vertical adjustment of a waveform is performed using volts per division. A grid on the screen indicates the voltage value set using the dial. When the probe attenuation ratio is 1:1, the voltage is shown directly. But when the attenuation ratio is 1:10, the value is multiplied by 10. The keyboard extender is used to pull out the keyboard so that the circuit board located beneath it can be checked. Casio supplies the flat cable and PCB connector separately, so the flat cable must first be cut so that the number of wires is equal to the number of pins on the PCB connector. Next, solder the contact surfaces of the PCB connector and the flat cable together and wrap the soldered area with insulating tape to complete the job. Heat seal is used in installing the LCD. The LCD is connected to the PC board by a sheet called a heat seal. When LCD segments do not light, the cause can be peeling of the heat seal or a faulty LCD. The LCD is attached using double-faced tape, which may be difficult to detach in some cases. Applying alcohol can help make this relatively easy. First, remove the heat seal from the LCD and the PC board. After removing the heat seal, clean carefully with trichloroethane. If the LCD is to be reused, clean it as well. LCD electrodes are difficult to see, but can be seen by tilting them so they reflect light. Align the electrodes with the black stripes on the heat seal. After heating the heat sealer sufficiently, continue to press on the heat seal for 3 or 4 seconds. Use care since the LCD can be finished if the bottom part is not flat. Use the same procedure to attach the other end of the heat seal to the PC board. Be sure that the PC board terminals and the black stripes on the heat seal are perfectly aligned. Next, we will look at some tools for removing solder. This is solder wick, which uses capillary action to remove molten solder. Here is a desoldering machine which uses a vacuum pump to remove the solder. This is a soldering iron used to remove soldered flat package LSIs. Just melt the solder with the tip, applying the LSI remover from the top, and remove the LSI by twisting the iron carefully. In some cases, LSIs are coated with an adhesive to prevent shorting due to condensation of moisture during low temperature tests in the factory. This adhesive can also be removed with trichloroethane. Here is another tool used to remove flat package LSIs. To use it, insert a small screwdriver under the LSI and blow hot air evenly on the pins of the LSI. The LSI will come loose within a few minutes. Applying too much force with the screwdriver can damage the foil of the PC board, so proceed slowly and carefully. Also, take care that the hot air does not melt plastic parts or lead wires near the LSI. Next, we will explain how to install flat package LSIs. First, clean the PC board of the removed section. Then, after aligning the LSI terminals with the pads on the PC board, solder the four corner terminals to secure the LSI. Finally, solder all of the remaining LSI terminals. Apply plenty of solder because, at this stage, it doesn't matter if there are any solder bridges between the terminals. When you are finished, use solder wick to remove the excess solder, making sure that solder bridges are not left between the terminals. This instrument is called a tuning meter. It is used to check the pitch of musical instruments. Now let's take a look at some actual circuits. In this video we explain general circuits such as CT430, CT320 and so on. First we will explain the keyboard. Two types of signals are necessary for key and switch input: the key common signal KC and the key input signal KI. The CPU generates signals KC1 to KC10 and sends these to the keyboard. Now let's try following the KC2 signal. This KC2 signal is output by the CPU and sent to PC board KY2 via PCB CN7. After entering KY2, the KC2 signal is then sent to the keys C2, C#2, D2, D#2, E2 and F2. When the D2 key is pressed, for example, the KC2 signal goes to KI3 and then returns to the CPU. When the KC2 signal returns through KI3, the CPU knows that the D2 key has been pressed. Here we see the KC2 signal. This is called a matrix table and shows the KC and KI signals for each key. All of the buttons and switches also input in the same way as the keys. For example, the KC10 signal normally is sent from the piano switch to the CPU. When this switch is turned on, this signal returns to KI1. Actual key construction is as shown here. A part called the key contact rubber is located beneath each key. This part contains conductive rubber, so, when a key is pressed, the key presses against the key contact rubber and short-circuits the contacts on the key PC board. The KC signals are fed to one side of these contacts, while the other side is connected to the KI terminals of the CPU. Next, let's see how the melody signals are generated. When the KC signal is received at the KI terminal, the CPU determines which key has been pressed and responds by sending 4 data signals to the melody LSI. All of the data signal lines are collectively called the data bus. The data from one key is transferred by sending it 3 times. The CPU constantly sends the set tones and data from each switch to the melody LSI, so signals like these can be observed by monitoring the data bus with an oscilloscope. When the melody LSI receives data from the CPU, it outputs 14 types of digital signals from O1 to O14. This is the O1 waveform. It will vary depending on the voice and the pitch. The 14 digital signals enter the digital to analog converter, where they are converted to a stepped analog waveform. The shape will vary depending on the voice used. With the CT430, the digital to analog converter consists of just one part. Almost all of the models use a circuit like this for the digital to analog converter. Since the LSI outputs only a small current, an inverter is used to increase the current. The current from the inverter flows through a ladder-shaped arrangement of resistors called a resistive ladder network. Whether or not the current flows is determined by whether the LSI output is high or low. Therefore, the output of the resistive ladder network is changed by this digital signal from the LSI. That is, low or high digital values are converted to analog values for the amount of current. This amount of current is then converted to voltage values by the operational amplifier. Depending on the accuracy of the resistive ladder network and the signal transfer speed of the inverter, distortion can appear when sounds fade away, making it impossible to obtain the correct envelope curve. Thus, we need to know what is an envelope. The envelope is the amount the volume of a sound changes with time. For example, the flute sound continues at the same volume as long as a key is pressed. This is the flute waveform. The line connecting the peaks is called the envelope. Consequently, the flute envelope is a straight line. The guitar sound decays or attenuates on its own accord, even though the key is held down. The envelope can be seen by slowing down the oscilloscope sweep time. This ends the explanation of envelopes. Now let's return to the digital to analog converter. As I mentioned before, in some cases it may not be possible to obtain the correct envelope, depending on the accuracy of the circuit. A bit compensator circuit is used to correct this situation. This is the correct Celesta envelope. If not correctly compensated, the sound fades quickly, or the sound is unnecessarily prolonged. These are called time lag noises. Here, the O1 terminal is connected to the variable resistor through 2 inverters. Signals are sent to the other terminal of the variable resistor through only one inverter. Consequently, positive and negative O1 signals are applied to both sides of the variable resistor, so positive and negative O1 signals can be added to the digital to analog converter output by turning the variable resistor. A positive signal is applied when the sound decays quickly, and a negative signal is applied when a sound is unnecessarily prolonged to obtain the correct envelope. The above is the operation of the digital to analog block. The stepped waveform output by the digital to analog converter enters the sample and hold circuit. This circuit eliminates noise called glitch noise included in the stepped waveform. A thin noise appears in each of the steps of the stepped waveform output by the digital to analog converter. This is called glitch noise and is the cause of high-frequency noise. This is the glitch noise. The sample and hold circuit is composed of one switch and one capacitor. This switch is called an analog switch and is turned on when the control terminal C voltage is high and is turned off when the voltage is low. One step of the stepped waveform is at least 25 kHz. Therefore, a 25 kHz pulse is supplied to the control terminal of the analog switch by the melody LSI. Consequently, the analog switch is turned on and off in a 25 kHz cycle. When glitches do not occur, the switch is on because the 25 kHz pulse is high and the digital to analog converter output passes the switch and charges the capacitor. The 25 kHz pulse is low when glitches occur, therefore the analog switch is turned off. Consequently, the digital to analog output containing the glitches cannot pass the switch. The capacitor then discharges, maintaining the sample and hold circuit at the same electrical potential. In this way, the sample and hold circuit eliminates glitches. The glitch-free digital to analog converter output next enters the filter block. The filter converts the stepped waveform to a smooth waveform. The waveform at the top is the filter input. At the bottom is the filter output. The filters also cut unnecessary frequencies according to selected tones. There are three different types of filters: a low-pass filter, a high-pass filter, and a band-pass filter, each passing a different frequency. The low-pass filter is mainly used with the Casio tone. This is the frequency response of the low-pass filter. In the low frequency range, the signals are passed, but above a certain frequency, it becomes difficult for the signals to pass. This point is called the cutoff frequency, or FC. With the Casio tone, the cutoff frequency changes depending on the tone selected, to cut the unnecessary frequencies. For example, for the flute sound, the cutoff frequency is set low to eliminate the high frequencies and produce a soft sound, since the flute sound does not contain a high-frequency component. The pipe organ sound contains high-frequency components, so the cutoff frequency is set high to pass these high frequencies. The cutoff frequency can be varied by turning on and off S1, S2, and S3. These switches are controlled by the I01, I02, and I03 signals from the melody LSI. The melody signals output by the filter go to the JE4 terminal. This view of the terminal indicates that it is connected to the AS1M PC board through the 4 pins of the flat cable. The arrow indicates input or output. This is the AS1M circuit diagram. The melody signals from JE4 go to switch S1. This switch is controlled by the stereo chorus switch on the console panel. Turning off the stereo chorus switch turns on S1. The melody signals pass S1, enter the right and left channel mixers, and are heard in monaural. Turning on the stereo chorus switch turns off S1. With S1 off, the melody signals enter the stereo chorus circuit. With the Casio tone, almost all of the stereo effect is created using a delay element called a bucket brigade device, or BBD. The BBD stereo effect does not produce a clear position for the sound, but, by delaying the signals, the sound can be reverberated to produce the stereophonic effect. Sound signals can be delayed when they pass through the BBD. The delay time is determined by the clock pulse frequency. With the Casio tone, stereo can be made more effective by increasing or decreasing the delay time. The low-frequency oscillator, LFO, generates a low-frequency triangular waveform. The voltage-controlled oscillator, VCO, oscillates in relation to the input voltage. When the voltage of the LFO output signal is high, the frequency is high. When the voltage is low, a low-frequency clock pulse is generated. This waveform is the LFO output, and this is the VCO output. When the stereo chorus switch is on, S2 is also on. Therefore, the delay signal from the BBD passes S2 and enters transistor T10. The collector of T10 outputs a reverse phase signal which enters the left mixer, while the delay signal output from its emitter enters the right mixer. That is, when the sound on the right is loud, the sound on the left is low. When the left sound is loud, the right sound is low. S1 is off at this time, but the sounds which are not delayed pass through the 3.3 kilo-ohm resistor to lower the sound level, enter the mixer, and can be heard from the center. Next, we will explain how to create accompaniments. First, the bass sound. The bass sound is created by mixing pitch and envelope signals. The pitch signals are output by terminal O38 of the CPU, and the envelope signals are output by terminal O44. The envelope signal from the CPU has a square waveform, but a smooth rise and fall are obtained by the charging and discharging of capacitor C. This is the bass signal. The envelope can be seen by delaying the sweep time. The bass signal enters the filter where the square waveform of the pitch signal is converted to a triangular waveform. The waveform at the bottom is filter output. Chord sounds are created in the same way, but since they are combinations of 3 or 4 sounds, the sound is created by mixing 4 pitches and 4 envelope signals. This is a mixed chord signal. Next, we will explain how percussion sounds are created. There are 2 types of percussion sound which are oscillating sounds and white noise. Bass drum, low and high congas and clavis sounds are created by oscillating sounds. Cymbals and hi-hat sounds are created using white noise. And snare drum is a mixture of oscillating sound and white noise. With the CT430, percussion sounds are created by an LSI, but we are going to explain the discrete circuit using the CT320 circuit diagram. Oscillating sounds are created by an oscillation circuit. The trigger pulse output by the CPU is emitted from the collector of the transistor, is time delayed by resistors and capacitors, and is fed back to the transistor base, causing it to oscillate. The oscillation frequency is determined by the resistance and capacitance. The feedback current drains to the ground little by little through the transistor emitter and variable resistor. Therefore, the oscillation waveform gradually becomes smaller. The attenuation time of sounds is determined by adjusting the variable resistor. The top waveform is that of a high conga, and the bottom waveform is that of a bass drum. Now, let's turn the variable resistor of the high conga circuit and see how the attenuation time varies. The cymbal and hi-hat sounds are created with white noise. White noise is noise that contains components of all frequencies and sounds like a hiss when output by the amp. The cymbal and hi-hat sounds are created by shaping the white noise in the cymbal and hi-hat circuit. The accompaniment LSI outputs white noise and trigger pulses. The trigger pulse is changed to a tapered waveform in the shaping circuit and mixed with white noise to create the cymbal and hi-hat sounds. The difference between the cymbal and hi-hat sounds is the time for which they are sounded. The cymbal sound is longer than that of the hi-hat. The snare drum sound is created by mixing oscillating sound and white noise. Oscillating sound is shown at the top and white noise at the bottom. The signals for melody, percussion, bass and chords enter the left and right mixers where they are mixed. After being output by the mixer, these signals pass through the main volume control and enter the power amp. After being amplified by the power amp, the signals are output from the left and right speakers and are heard as sounds. To end part 2, we will explain the power circuit. This circuit is important because it supplies voltage to all of the other circuits, so it must be fully understood. This is the battery-driven Casio tone power circuit. Transistors perform switching operations and can be replaced by switches. The APO signal is supplied by the CPU and is high when the power switch is on. This turns on both T1 and T2, so power is supplied from the battery to the power amplifier, as well as to the collector of transistor T3. T3 and the Zener diode regulate it at plus 5 volts. To conserve the batteries of the Casio tone, an automatic power-off APO function is provided to automatically turn off the power when a key is not pressed for a certain length of time. This operation is controlled by the signal APO from the CPU. When the APO signal is low, this turns off T1 and T2 and stops the plus 7.5 volt and plus 5 volt power supplies. Have you noticed anything about what has been explained so far? That's right. The APO signal from the CPU is necessary to operate the power circuit, but the CPU cannot operate because it cannot receive the plus 5 volts power supply from the power circuit. Thus, T1 is forced to turn on when the power switch is turned on. The circuit that does this is formed by capacitor C and resistor R. When the power switch is turned on, the voltage from the battery passes through the C and R differential circuit and supplies a single pulse to turn on T1. When T1 turns on, T2 is also turned on. This 5 volts is then supplied by the power circuit to the CPU so the CPU can output the APO signal. This completes the explanation of the power circuit and also ends part 2. Part 3. Adjustments. Bit compensation adjustment is performed when digital to analog converter parts are replaced or when distortion appears at the ends of attenuated sounds. Connect an oscilloscope to the digital to analog converter output. The digital to analog converter output waveform is at a low voltage level, so lower the voltage range setting of the oscilloscope. The waveform may be blurred and hard to see in some cases. If so, it can be seen clearly by passing it through a 2 kilo or 3 kilo ohm resistor. When a key is pressed, the digital to analog converter output waveform appears at top and bottom, gradually becoming smaller and finally disappears. Adjust so that both disappear at the same time. Here the top waveform remains, indicating that the sound is prolonged more than necessary. The bottom waveform remains in this case. Adjust the variable resistor of the bit compensator so that both the top and bottom waveforms disappear at the same time. This is the adjustment for the attenuation time for percussion sounds. Let's observe the percussion output on an oscilloscope. Notice that there are percussion sounds that are not heard because of the rhythm. Imagine the envelope connecting the peaks. Let's select one of the peaks and measure the voltage. Almost any peak can be selected except for the first because the voltage is unstable. Next we will find the point on the envelope curve where the voltage is 1/2 of that of the selected peak. Adjust the time between these 2 points to the values shown in the chart in the textbook using the variable resistor of the percussion circuit. BBD speed adjustment. Let's observe the LFO output of the stereo chorus circuit on the oscilloscope. Adjust the variable resistor of the LFO circuit so that one cycle of the triangular waveform appears in the time given in the textbook. For the CT430, this time is 166 milliseconds. This ends this videotape presentation. Please feel free to send in any technical questions or requests concerning the Casio tone.